Okay, so we're live. So today we're going to go over this DSP introduction that was released about a week ago. I'm really curious, less than a week ago. DSPs are something I'm not as familiar with or skilled with when it comes to FPGA development. I, I mean, I can do a lot with, I guess, maybe stuff I do is inferred, like multiplication, division, fixed point, stuff like that may be inferred by the DSPs, but I don't necessarily use the DSP primitives, and I want to be able to understand the, I guess, the limitations of the DSP so you can engineer your hardware, your HDL, to use them in the most optimal way. I want to be able to learn how I can overclock them. DSPs can usually be clocked about almost twice as fast as your logic. So a lot of times you can almost do like a double data rate where you are inputting, you are doing new inputs to a DSP block on the positive edge and on the negative edge. So you can overclock the FPGAs in comparison to the HDL. And I'm curious to see what I can learn from this thing. So let's see. Welcome to my series about math and algorithms. Multiplication of DSPs is this thing. He also has new to series. There's numbers in Verilog. Let's see if there's let's just poke real quick at these older ones, see if they're binary and Verilog, binary, variable widths, literals. Yeah, these are just all things. Animated shapes, FPGA. He has a GPU one, right? So we go to graphics, right? Or we go to about animated shapes. He has like a FPGA. It's in the sitemap. FPGA graphics and hands-on tutorials, introduced Pong, hardware sprites. This I want to go through this as well. Okay, so yeah, let's start with this. Maybe afterwards we can dive a little bit into FPGA graphics. That would be interesting. So FPGAs incorporate DSP blocks. These are ASICs. ASICs, fast Fourier transforms, finite impulse response, FFTs, FIR filters, multiplication. Okay, so I guess we're targeting straight multiplication in this explanation. Yes, DSPs are ASIC application-specific primitives in your FPGA, and they will outperform LUTs and flip-flops, both in utilization, latency, power, bandwidth. So use your DSPs when you can. I completely agree. Let's take a look at multiplication. Different sizes. This is kind of interesting, right? Because I was talking to a professor, and they were doing an 18-bit wide processor, or it was a professor from Europe, I think. He was designing an 18-bit processor for the Series 7 FPGA, so it fit exactly with the DSPs. So, like, that's an idea where we talk about designing our HDL to match what is the capability of the processor or of the FPGA. So then we can design like a processor that's the exact width of a DSP, and that can help us achieve better performance, better utilization, while keeping the accuracy in our algorithm that is sufficient. On different parts. Okay. So what part I have on the? Oh, he added the AUP 10P here. That's a very new product. I'm surprised that he did that one. So this is a product that you see on a lot of FPGAs, and the 85 and the 25. I think I have some of these on some other FPGAs as well. The 200T, I don't have the 200T, I have the 35T, which is basically linear from 200T. I do have a Spartan 7 FPGA coming next summer, or in the summertime, but that's a ways out. I do want to work with the AU25. I have an AU25P on order, so we'll have to see how that works. Yeah, me too. RTX Ultrascale Plus. I would love to see RTX Ultrascale Plus. So right now let's dive into the Series 7 DSP slice. So this goes to documentation, yeah, of Xilinx. Let's see if we can find a block. Right here, our basic block functionality. We have 4 inputs that are flip-flopped. Pre-adder, then we have another flip-flop. We have a multiplier, a flip-flop, and then it looks like a mux that determines the outputs. Okay. Human logical unit. That's a basic slice functionality. Do we have a more sophisticated block? Oh, here we go. This is the more complicated DSP diagram we can go study, right? So we have the inputs. We have a pre-adder, just a multiplier to here. Then we have an X, a Y, a Z, different zeros and ones, input coming here, shift registers into these different values. Pattern detect, interesting. So yeah, there's a lot we can do in this device. And they break down the adder so we can look at them again. Yikes. Does this have the AU25P on it? Page down. I want to see that they have the breakout. So here it looks like a bit wider. Have a new W there and some different, slightly different functionality. They have the part here. Is this no? What's the? Do they have the other part description like the other one? It doesn't look like they do. So, we got 77-page document there, 58-page document there. So lots of details on DSPs. Really, interesting stuff. Using DSPs in designs. Yes, so we can explicitly instantiate the DSP primitives, or we can infer them using multiplication or HDL. Very important. I want to get good at the primitives. I mean, I guess I've inferred these a long time. We have a YOSYS design. You'll need to explicitly enable DSP inference using the DSP object, for example. You can disable this. So YOSYS is open source tools, but let's see what some examples. Multiplication examples. To create and practice examples that combine simple math functions with graphic outputs. If you have an FPGA board, yes, Gen 01. System design features in this post are available for Project Explorer Git repo under the MIT license. Okay, let's go pop a quick look at this thing. So I think it's under his math demos. Hello, math multiplication. Yeah, oh no, that's just, these are the math demos. Yes, so these math demos. So I guess we want to look at the XC7 board. Yeah, I have the original. I have the original one, not the 35K. I have the original. There's no. Okay, so yeah, let's pop a look right here, right? Vivado, pop graphing, Vivado, great project. Not a fan of Verilog. I wish I was more of a fan. I like VHDL better because I'm a terrible person. Don't ask me why. I don't necessarily think VHDL is better. I just like it better. I don't think I'm necessarily right on that decision. Okay, so these are clocks and display, functional coordinates, the function to graph. So it looks like so that like it has a graph there. Where is this? Is it like some source code for these things? Oh, function. Okay, what function are we dealing here? Right? Function squared. So sweet. Let's go see what function squared looks like. Function squared. So we have a clock, we have the X and the Y and the R, and okay, so it looks like we're just drawing a square based upon different parameters. Okay, so back here, yeah, X squared is larger than explained below. So using integers, each picture represents one whole number. We square X, the value equals to the largest bit on the screen. Assume each vertical pixel represents one big more. The pixel we scale a parameter. In this case, the scale, so each pixel represents 256. Here's a sample of top model to drive it. Okay. Yeah. Yep. We just look this over. We can build the demos from the thing. Here's what the bare layer simulator looks like. Yay! We get a half circle. Yep. Circle. I thought this would be a little bit more in depth, but this seems pretty basic. Let's compare the timing and logic for the two versions of the designs on different FPGAs. Squared 1, squared 2. Target, okay. Cycles. No, using the newest Vivado. Good for you. Okay, yeah. Force negative slack. As long as force negative slack is above 0, you're good. For circle. Cubed. What's the cube one? Do they have an output, the cube? Okay, yeah, so it looks like this has we've reached the end of this. I thought we would have more detail about the DSPs in here, but yeah, here's a good example of using DSPs to do graphs. We should do a TI-89, right? We should develop a TI-89 for an FPGA. That'd be fun. Yeah. Okay, so this is all interesting. This seems like a good website to become more familiar with what FPGAs are capable of, especially I think besides the HDL, like a good FPGA designer is going to know the primitives that are on the FPGA. We're going to know if we have a LUT4 or LUT6. We're going to know the different flip-flops, the shift SLRs, the shift registers. We will know about the other primitives, the DSPs, VRAMs, the ultra RAMs. Sometimes there's some FIFO primitives, the IO30 primitives. Sometimes you'll have primitives for like the PCIe and stuff like that, or even the special debug features. For Xilinx, there's a lot of unique debug features with JTAG, BScan, the DNA register, stuff like that. That if you're aware of the capabilities, you can figure out some really fancy uses. So let's go check over graphics, right? I want to see his graphics section. Intro to FPGA graphics. Okay, what we got here? I have that board, I have that board. So we got options. Interesting. I like that little thing. Yes, it's talking about the horizontal sync and the vertical sync of the screen. Good explanation there. The screen running on time. Wow, we do this in our 220 class. We do this at BYU. This would be a great thing to help people understand it better. Yeah, I should send this to Dr. Worthen. DVI. Just keep rolling. Okay, what's possible? Okay. I'm just curious. I really want to do like a some here do hardware sprites. I would love to be able to do 3D graphics on an FPGA. Someone did that recently, and I would love to see that. Is there anything worth picking out? Sprites, video timings, Pong, lights on the screen, 2D shapes, animated shapes. Okay, let's go to the last one. We might have to end the video early because I don't really got anything else to talk about. We went over what I wanted to talk about way too quickly. That's okay. Maybe we go do the advent of code. Maybe I will end this video. We'll do a quick impromptu advent of code on the Kira board. I got to plug in the Kira board and get Jupyter up and running on it. But yeah, we'll get that going. Is there anything useful in here? Okay. So I think we're good here. I was interested in the DSPs, but let's just give this guy a let's go to the main webpage. This is a great blog. It's in the description. Stop by, look at it. Introduction to some basic FPGA concepts that you can start doing a fun hobby project. Graphics, the math. Let's put Doom into the FPGA in the HDL. That'd be great. Hardware accelerated Doom. That would be a fun little project to do. Otherwise, I think I'm going to jump off here, plug in my keyboard, and see if we can get the Advent code going on. So stick around if you want. We'll get